number 1 of e-learning from COVID-19. So hopefully you guys are all home safe. And I'm going to go over this PowerPoint with you guys. It's C.5. So by now, before you watch this video, you should have outlined C.5, so you kind of have an idea of what's going on. This is all about populations and estimating population size and growth. So let's get this party started. See if this will work for us. Here we go. Alright, so first understanding, exponential growth occurs in an ideal and unlimited environment. So you can take a look. Hopefully you can see my mouse. This is actually a population of bacteria. You could replace this curve with the current news of the virus and its spread, although it's not quite population, but spreading, shows exponential growth. So the more that the more individuals in the population, the faster it grows. Now this only happens under ideal conditions. So you have to have enough space, resources, everything's got to be unlimited so that the population can continue to grow. Once you have competition or limited resources, then your population will start to level off. So they had some examples here. Throughout the 1800s, hunters decimated American bison populations. By 1889, there were only about 1,000 bison left. The U.S. government, along with private landowners, started protecting the bison, so you can look at their population growth down here. And since the time that they've been protected, the population has grown exponentially. We now have a pretty healthy population of bison. Let's see here. Oops. So let's move on. Here's some examples of exponential population growth. The human population has been growing exponentially for quite some time, since the origins of agriculture. And you can see here where our population has taken some dips, the bubonic plague. You can see the Industrial Revolution, how the population starts to grow really quickly again. I don't know what's going to happen in the future. It doesn't seem to be reaching any endpoint as far as our population growth. We've got unlimited resources. We can keep our sick healthy and well, or at least alive. So here we have the definition of a population. You've already learned this from your previous units. A group of individuals from the same species in a given area at the same time. For most populations, especially in the wild, it's really hard for us to measure the number of people in that population. So what we'll do instead is we'll do a sampling technique. So kind of like we talked about last week, only this time we're going to be sampling in order to measure the number of people in the population. One of the ways we can do that is something called the Lincoln Index. The Lincoln Index uses a formula. We're going to capture some snails, we're going to mark them, then we're going to turn them back loose in the wild, and then we're going to recapture some snails and see how many snails we capture in our second capture that were captured in our first. So hopefully this will make sense. The Lincoln Index only works if you follow some guidelines. First one is when you capture them, you can't harm them. Oh no, look at the little snail down here. Yeah, we don't want to hurt him. Also, we have to make sure that when we capture them, they don't learn from that process. So we can't have them going, ooh, I'm not going to go near that trap again because, like, you know, I might get captured. Also, we have to keep our, hold on one second while I get my dog. Okay, we're back. This time with help. Say hi, buddy. Everybody, this is Chip. Look, Chippy, it's a snail. You see the snail there, boos? Huh? When we mark the animals for our sampling, our population, to figure out how many are in the population, we have to make sure that that mark doesn't make them more likely to be caught by predators. We have to make sure that mark isn't toxic, doesn't affect their sexual attractiveness for reproduction. We have to make sure that the mark basically doesn't hurt or help them at all, and that they don't learn how we catch them for marking. So let's take a look at some ways that population can be limited. So here they are, this list. Food. What do you think, boo-boos, huh? See? Food, space, disease, predation, environmental change, viruses. Ooh, viruses. Ew, don't lick me. You're nasty. Okay. Senescence, which is death from old age or illness related to age. If a population has unlimited resources, it will grow exponentially, but most populations in our ecosystems we find have something that will limit their growth, and so the population will basically level off, and that's where our carrying capacity is, which is this K. Slide. The first set here, this is density independent, so this is meaning like a factor that might affect population growth that is not impacted by the number of individuals there. Whereas this one, which is density dependent, most of the limiting factors are density dependent, which means that the number of organisms in your population, individuals in your population, affect how big of effect these factors have. Oh, you want to get down? Huh? You gotta be quiet though. I'm trying to make a video. Okay? Can you be quiet, please? Thank you. Okay, you got one chance. Okay, so we got 4 main factors contributing to our population growth. Immigration, which are individuals moving in. Birth rate, which is natality. Mortality, death. And immigration, which is individuals moving out. For the test, make sure you know the difference between immigration and immigration. Which of these 4 things increase the population and which decrease the population? They have a graph here that shows like when your immigration and natality is greater than your immigration and mortality, your population grows. When they're equal, your population stays relatively constant. And then when immigration and natality is less than immigration and mortality, your population will decline. These things are all kind of like logical, so I think on a test you can probably figure them out. So we're going to go here, look at the population. Okay, the graph has 3 phases. You have an exponential phase, which is the beginning where it's growing really fast. Your transitional phase, which is where the population starts to slow down, but it hasn't plateaued yet. And your plateau phase is during the flat part. You can see the relative immigration, natality, immigration, and mortality on the right-hand side in comparison to each phase of when they're equal or when they're greater or less than. Here's another look at those and a more description here. You guys can pause this and read through these if you'd like, but I think you probably got the hang of it. Now, there are 2 categories of limiting factors. The first one are top-down factors. These are things that come from above the food chain that limit the population growth. And bottom-up factors are things that come from the bottom of the food chain and limit the population growth. So like if resources, for example, food is an issue, then it would be a bottom-up factor. And if like a population is limited by the predators in the area, that's a top-down factor. We've already learned the importance of predators in controlling population. We talked about keystone species in our purple sea star, the otter, I think the alligator, and some other keystone species that we mentioned. Predators are important in controlling population. When you don't have these predators, these populations of herbivores get out of control, and then we lose our autotrophs, so that's bad. This particular understanding I find is kind of interesting. Bottom-up control of algal blooms by shortage of nutrients, and top-down control by herbivory. So what's happening here is these algal blooms in the water can be controlled by not introducing the nutrients into the water. So if we regulate nutrients being poured into the water, such as runoff and fertilizers or things like that, we can control the population of the algae in the water and hopefully slow or get rid of eutrophication. We can also get rid of the algae by introducing something that eats algae. And so they have, I'm pretty sure, a fish here. Here we go. The parrotfish. The parrotfish are herbivores that live on algae. And so they're great to introduce into ecosystems where algal blooms are a problem. We're not going to worry about the duckweed. Guys, your duckweed probably isn't going to make it. If we even go back to school this year, the duckweed, yeah, we're going to have to count this experiment up to a loss because they're probably sitting in my room right now dry in their cups. So sad. Okay. Maximum. Check this out, guys. Okay, Nugget, I don't want you to poop on me. Look at how big Nugget is. Nugget, you're so cute. You're so big. Say hi, everybody. Whoa, 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 whoa. Back. Back, 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 back. Okay, Nugget's gotta go. Come here, Kylie. We're babysitting a dog that thinks she eats chickens. Don't ya? Okay. Oh. Gotta go. You guys stay down there. Oi. Okay, guys. That's all for now.